Hello everyone, welcome to the course Data Structures. This is Thulasi Chitra, Associate Professor, Department of CSIT, MLR Institute of Technology. In today's session, we are going to discuss about the B trees. Let us see the overview of today's session. We will be seeing about B tree introduction and followed by B tree operations. What are the different operations we are going to discuss? Insertion, searching and deletion. These are the three different operations we can perform on B trees. And we are going to solve an example on B tree insertion also. Okay. Let us see what is B tree. Let us see what is B tree. B tree is also known as self-balanced search tree. As AVL tree is one of the alternative for BST, and like that B tree is also a self-balanced binary search tree in which every node contains multiple keys and has more than 2 children. Up to now we have seen a binary tree. A binary tree is having only 2 children. But here in B tree, a node consists of many children like this. More than 2 children. Okay, it may have more than 2 children. And multiple keys also that will have. Every node contains multiple keys and has more than 2 children. And in search trees like binary search tree, AVL trees, red-black trees, etc., every node contains only one value. One value is nothing but whatever you are representing here. This is nothing but the key. And maximum of 2 children, as we have seen like this. But there is a special type of search tree called B tree in which every node contains more than one value and more than 2 children also. Okay, more than one key value it may have, more than 2 children also it consists of. Suppose you consider like this, I can have more key values, and for this it may have more children also. Okay, this is a B tree. You can find the difference between what is binary search tree and what is B tree. And this B tree was developed in the year 1972 by Bayer and MC Wright with the name Height Balanced M-Way Search Tree. First, it was developed by these two people, Bayer and Wright. And the name that was given for that is Height Balanced M-Way Search Tree. Later on, it is named with B tree. Okay. And here it is going to follow some properties for that is balanced tree or B tree. What is the properties it has to maintain? Balanced M order way tree. M order. M is nothing but the order of the tree. Suppose it may be of order 3, order 4, order 5, anything you can consider. Based on that M, it depends. It depends on the M value we are going to construct the B tree. And it is generalized form of BST in which each node can have more than one key and more than 2 children. As we have seen in the previous example, it may have more number of keys and more number of children also. And all key values in a node must be in the ascending order. Whatever the key values we are going to represent, all will be placed in the sorted order, in the ascending order only. And all leaf nodes must be at the same level. Whatever the leaf nodes you will be having, all will be at the same level. That may be of level 2 or level 1 or level 0 itself, right? You may have all the leaf nodes will be at the same level. And when you are going to construct a B tree, you have to follow all these properties. What are the properties you have? Every node has maximum M children. Suppose if I am going to have a node M, for that you have M children has to present. And minimum children can be, for leaf node it will be of 0, if it is of a leaf node, you don't have any other nodes that can be connected, right? That is a leaf node, right? For that, it will be of 0, and for root node, it will be 2, and for internal node, it will be CL of m by 2. Suppose I am going to have m equal to 4, right? Every node has, consider I have 4 children. Internal nodes can be CL of. CL of means we are going to take the highest value, 4 by 2. 4 by 2 is nothing but 2. That means CL of means we can have up to 3. CL of the highest value we are going to take, right? And every node has maximum of m minus 1 keys. If I have m number of nodes means m minus 1 keys I need to present. And minimum keys for the root node will be 1, and all other nodes will be CL of m by 2 minus 1. Right? Based on these conditions, based on satisfying all these properties, we are going to have the B tree to be constructed. And these are some of the properties of B trees. You need to check all these properties, right? All the leaf nodes, the first property of B tree has to be all leaf nodes must be at the same level. Okay, that is the first property. All nodes except root node must have at least m by 2 minus 1, that is CL of m by 2 minus 1 keys, and maximum of m minus 1 keys. Okay, and all non-leaf nodes, that means the internal nodes except the root node, must have at least m by 2 children, right? M by 2 children it has to present. If the root node is a non-leaf node, then it must have at least 2 children. If it is the root node is not a leaf node, then it must have at least 2 children it has to present. Okay, with all these conditions has to be applied when you are going to construct the B tree. There you will be knowing that all these cases. A non-leaf node with the n minus 1 keys must have n number of children. Okay, and all the key values in a node must be in the ascending order. With all these properties, we are going to construct or insert elements into the B tree, right? And B tree has the following operations. One is insertion, deletion, and search. These are the 3 operations where you can perform on B trees. First, we'll be looking into the B tree insertion. How we are going to insert the elements into the B tree. Here, every time the elements, observe, in a B tree, a new element must be added only at the leaf node. Not directly on the root node we are going to insert element at the leaf node. That means the new key value is always attached to the leaf only. That means when I am going to insert a node, we will see the example, right? When I am going to insert a particular node, that should be inserted only in the leaf node, not at the root node. Okay. Now, we will see the steps how we are going to perform the insertion. The first thing, step, check whether the tree is empty. Yes, if the tree is empty, then we are going to proceed with these following steps. If the tree is empty, then what we need to do? Then we create a new node with a new key value. Okay, and insert it into the tree as a root node. If I am going to have the tree is empty, that node will be inserted as the first key, and that will be considered as a root node. If the tree is not empty, means it consists of already some values or some nodes. Then find the suitable leaf node to which the new value is added using binary search tree logic. That means if you have already some elements, we need to check for the location in the leaf node where I need to insert in the binary search tree condition. At the same time, it has to placed in the sorted order. Okay. This is the third step. And fourth step, if the leaf node has empty position, add the new key value to the leaf node in the ascending order of the key value within the node. If the leaf node has some empty space, right, you can insert some new element into that leaf node, you can insert it. Otherwise, inserting also could be done in the ascending order, right? And if the leaf node is already full, then what we need to do? Split the leaf node by sending middle value to its parent node. We are placing the elements in the sorted order, and we are going to split that leaf node in the middle, and we are going to move that particular element to the parent node. Repeat the same steps until the sending value is fixed into a node. We are going to repeat this process until it has to reach to a particular node. If the splitting is performed at the root node, then the middle value becomes the new root node. Yes. If it is splitting at the middle, then that becomes the root node, and from there it has to have the left and right subtrees for the tree. And the height of the tree is increased by 1. If it is moving up to the 1 level, then the height of the tree also is going to be increased. Like this way, we are going to perform the insertion. These are all the steps are going to be included in solving one problem. Okay. Let us consider or construct a B tree of order 5 using the following numbers. Right. Here they have given order 5. I told you we can construct a B tree of order 3, 4, 5, any of order. Based on M it decides, right? Based on M value, order M order that represents in which order we are going to construct our tree, right? That decides how many keys should be present, how many children should be present for our B tree. This is of order 5. Because of that, we can have order 5 means at most we can have 4 keys. 4 keys that it should have, and the internal node should have at least 3 non-empty children, and each leaf node must contain at least 2 keys. As we have seen, we have given some conditions, seal of m by 2 and seal of like this way we have seen seal of m by 2 and seal of m by 2 minus 1. This will return these things. What is the leaf node? What is at least how many keys that has to be present in the leaf node? At least how many internal nodes it must have, right? And if we can see 4 keys, that is order is 5 means most of the things which it should have is 4 keys. 4 keys we can store, and at least internal node should be of 3. Internal node should have 3 non-empty children, right? 3 non-empty children, that is 4 by 2. 4 by 2 is nothing but 2. We are going to take the seal of it. That means the next value, that is 3. Next, 4 by 2 minus 1. That is 3 minus 1 is nothing but 2. Based on this, it will decide how many internal nodes it should have and how many leaf node, at least how many internal nodes and at least how many leaf nodes it must have, right? Now, taking the elements, here first 4 keys directly we can place, and that keys also should be placed in the sorted order. From this list, first select the 4 keys. 4 keys are selected and place them in the sorted order. What are the elements we have? 3, 14, 7 and 1. Place them in the order 1, 3, 7 and 14. These are the elements to be placed in the sorted order. Now, after inserting all these are the key values 1, 3, 7 and 14, and these are the children for it. 4 keys and 5 children. Maximum of 5 children we can store in here. And what is the next element I need to insert? I need to insert the element 8. I need to insert the element 8. Where I need to insert the element 8, observe 1, 3, 7 and 14 I have. As per our condition, we need to insert the element in the sorted order. Right? After 7, I need to insert 8. Now, after inserting this, but here I have the chance of placing only 4 keys, but I can't place 5 keys. So, I need to divide this into 2 halves, and I need to move this element to the next level. to the parent level. To the next level means upper level. Now based on that, what I am going to get? I am going to get 7 as the parent node, and the remaining 1, 3 and 8, 14 all becomes the child nodes. Right? 7 becomes the parent node and 1, 3 is the left of 7 and right of 7 is 8 and 14. And again it has to follow the same property of our BST. Now we need to insert the next element is, after inserting the same case, the next element where we can insert is 5, 11 and 17. First I am going to take 5. Where I need to insert 5, check with the root node 7. 5 is less than 7, so we are going to insert 5 here. Next we have 11. 11 is greater than 7, so we are going to insert after 11. Right? But in between, but we have 8 and 14. In between that, we need to place it in the sorted order. Next we have 17. 17 is going to be placed on right of 7. Why? Because 17 is greater than 7. Right? Done. Next, what is the next element I need to insert? 13 has to be inserted. 13 is going to be inserted. When we am going to insert 13, check for the place where I need to insert here. Here, as per this condition, I need to insert 8, 11, 13, 14 and 17. Right? But 13 is the middle element. Right? I don't have the place to insert all 5. Right? So that what I need to do, I need to move one element up. I need to move one element up. That means I need to move to here 13. And the left of 13 should be 8 and 11 and right should be 14 and 17. Right? This split has to be done. As you can see. On left of 13 you have 8 and 11 and for right you have 14 and 17. This like this way we are going to split it. Then I need to insert the next element 6, 23, 12 and 20. First I want to insert 6. Where I need to insert 6? I need to check with the root node. 7 and 13 are there. But with 7 I am going to check first. 6 is less than 7. So I am going to insert on the left subtree of 7. Right. Next to 23 I need to insert. Check with 7. It is greater. So check with 13. It is greater than 13. So we need to move to the right of it. After moving right to 8, we need to check where it has to be placed in the proper position. It is already 14, 17, 20 is there. So I need to insert. This is not placed previously. Actually, this is the diagram. 14, 17 are there. So we need to place 20 after 7. 23 after. Here we don't have this element previously. 14, 17 and 23 is going to be placed. Right? Next, I want to insert to 12. Check for the right position according to BST. It is less than 13. So I need to move to left of this tree. So it has to be placed after 11. You have the place, right? 4 keys can be placed here. So we are going to place it as this one. Next, 20 has to be placed. 20 is greater than 13. Move to right of it. Already have 14, 17 and 23 are there. So I need to place this 23 in between 17 and 23. This is the right place to place the element. Here no need of any splitting. Why? Because we can place 4 keys at a time in this children. Right. The next node where we are to insert is 26 to be inserted. Now check 26 where is greater than 7, greater than 13, greater than 20. Now I need to move to right of it. Right of it. And if you can check here, right of it means this part. 14, 17, 20, 23 and 26. Now 20 has to move up. And left of 20 is 14 and 17 and right of 20 is 23 and 26. Yes, I can place one more element here, 20. But on left of it should be this one, 14, 17 and on right of this one is 20 and 23 and 26 has to be placed. So how that split can be done? Just observe. 20 moved up, 14, 17 is the left of 20 and 23, 26 is the right of 20. That was done. Next, I need to insert 4. When I want to insert 4, I need to check with 7. By checking with 7, here it is less than 7. So I am going to place in this left subtree. In the left subtree, I have already 4 keys, but I am unable to insert it into this. So what I am going to do, I am going to insert this one 1, 3, 4, 5, 6. But it is the middle element where I can move this 4 to the next level, upper level. So I can have the accommodation here to place 4 here. It is 4, 7, 13, 20 is on the top level, and 1 and 4, under 4 again we have 2 splits. 1, 3 becomes the left child and 5, 6 becomes the right child. Yes, now this is done. Now at last we have one more node to be inserted, that is 19, where I need to insert 19. Observe in this. Here all 4 keys is 19 is going to be inserted. After 19 is greater than 4, I can't insert here. 19 is greater than 7, no, not possible. 19 is greater than 13 but less than 20, but I can go to here, right? I can go to either right of 13 or I can consider left of 20, where I can insert 19, right? Now, when I want to insert 19, what are the elements you have? 14, 16, 17, 18 and 19. These are the elements where I can have. But I can't place 5 elements into this, so I need to move 17 to top. When I am moving 17 to top, what happens? 4, 7, 13, 17 and 20. Here also I can't accommodate 5 elements. But because of that, I need to perform the split of these two. Here also we are going to perform the split. So what we are going to get? 13 becomes the root node and 4 and 7 becomes the left of it. 17 and 20 becomes the right of it. Now we can check here how the diagram will be. 13 becomes the root node, 4 and 7 is the left child, and 17, 20 are the right child. And according to this, these elements are also has to be placed. Okay. For 4, 1 and 3 are the left children. 5 and 6 are the right children. Otherwise, we can consider 7 left children are 5, 6 and 8, 11, 12 are the right children. And here 17, 20, on left hand side you have 14 and 16, on right hand side you have 18 and 19. And for 20, on right hand side you have 23, 24, 25 and 26. All these elements are going to be placed. Like this way we are going to perform B-tree insertion. And let us see the summary of this session. We have discussed about B-tree introduction, what is B-tree and all those things, what are the properties under that to construct a B-tree. And we discussed about B-tree operations also, that is insertion we have discussed, searching and deletion we need to discuss in the next session. And these are the different operations where we can perform on B-trees: insertion, deletion and searching. And at last, we have seen one example of B-tree insertion also. If we have given some elements, how we are going to perform or construct a B-tree. Okay, I hope you understand this concept. You can try to solve the same example, and after solving the same example, you can try for the other examples also. Okay.